Let's begin. This is our term project, a from-scratch comparison of an LSTM and a transformer encoder on Jaejun. I'm Byeongha presenting with Jaejun Lee. Our goal is not the highest accuracy. We want to understand how these two architectures behave differently when trained under the same conditions. Here is our question. If we fix everything else, such as the data, vocabulary, optimizer, and a budget, then the only thing left to explain a difference is the architecture. We use Agenius because it's clean and balanced. The key point, two models can both reach 91% yet fail on completely different inputs, and that gap is what we study. Now the data. We split Agenius into 108,000 training, 12,000 validation, and 7,600 official test examples. We touched the test set only once at the very end because using it earlier would make our final number dishonest. The classes are balanced, so accuracy and macro effort move together, and a fixed seed keeps everything reproducible. Both models get identical input, lowercase word level tokens, and a 20,000 word vocabulary built only from training data. The interesting choice is the maximum length, which we measured, not guessed. 99% of articles are under 78 tokens, so 128 truncates almost nothing, while 256 only doubles the compute. So we use 128 and test 256 in the ablation. Padding is masked everywhere. Both models are built from scratch. The LSTM reads the sequence and max pulse over the real tokens. The transformer adds positional encoding lets attention mix all positions that mean pulse. The key detail is masking, so padding never affects the result. Both are about 3 million parameters dominated by the shared embedding, so any difference comes from modeling, not size. Think of this as our control checklist. The data, optimizer, batch size, epochs, loss, metrics, and seed are all shared, and the vocabulary is built once and frozen even when we shrink the data. So only the architecture varies, which means any difference comes from the architecture and nothing else. Then we deliberately vary three things, and that is the ablation. Each row of this table is a question with a hypothesis. We expect the higher capacity transformer to need more data dropout to help the small data transformer most, and 128 and 256 to perform about the same. Each axis changes only one thing, so the results tell us not just which model wins but why. Here is the data efficiency result. On the left, with only a quarter of the data, the LSTM is actually ahead, the safer choice when data is scarce. As data grows, the lines converge, tying near 91% at full data. The transformer climbs faster, gaining 4.4 points against 4.0, so it catches up but does not overtake. So hypothesis 1 is only partially supported. Now the other two axes. For dropout, the one clear win is the transformer at 25% data, where it gains 1.3 points, while everywhere else the effect is flat. That is our prediction exactly, because regularization helps a high capacity model starved of data. For sequence length, 256 never beats 128 by more than half a point at twice the cost, so 128 is the right default. Now the number we computed only once on the test set. The LSTM gets 91.14% and the transformer 90.99, essentially a tie. Validation and test almost match, so we did not overfit and the loss curves show both converge smoothly. The accuracy is honest, which raises the real question. If the two are tied, how do their errors actually differ? These are the two confusion metrics, and similarity is the point. Both handle sports and word almost perfectly, and both concentrate errors on business versus science and technology. That makes sense because a tech company's earnings story belongs to both. So the hardest part of this task is shared. It lives in the data, not in any one model. This is our most interesting slide. The two models miss almost the same number of examples, 673 and 685, but in different ways. The first two cases are shared and barely model errors. A trim marker story reads like technology news, and the Olympics one looks mislabeled. The real contrast is below. The LSTM's errors are scattered and idiosyncratic, while the transformers are systematic because business words like higher or oil markets pull it toward business. Same accuracy, very different error structure. To summarize, at full data, the two are tied near 91%, but the experiments tell us more. The LSTM is safer when data is scarce. The transformer benefits from more data and from dropout in that region, and the longer sequence length is not needed. The finding we value most is that they fare differently, one systematically and one idiosyncratically, which accuracy alone would hide. Our main limit is a single seed, so a multi-seed study is next. On AI use, we used Cloud Code to help with the scaffolding, the data pipeline, and the tests, but we verified everything ourselves and made all the key decisions. That concludes our presentation. Thank you for listening.